Okay, today's topic is rescaling equicontinuity. Okay, then we have a metric space X. This is a metric space, and I will denote Cxx, the set of continuous function f from x to x, continuous. Okay, we say a subset of Cxx is equicontinuous if for every epsilon positive there is delta positive, such that if the distance between x and y is less than delta, then distance between the image of x, image of y, less than epsilon for every f in capital F. We say it pointwise equicontinuous. If for every epsilon positive and for every x in x there is a delta x depending on x positive, such that if distance between x and y less than delta x, then distance between fx and fy is less than epsilon for every x, for every y, sorry, for every y in x, for every f, sorry, for every f in capital F. Okay. First, equicontinuity is equivalent to pointwise equicontinuity, but in compact spaces. Not true in general. In general, equicontinuity implies pointwise equicontinuity, but not conversely. Okay. Now I will present a characterization of pointwise equicontinuity as follows. Let x of x, this will denote the set of continuous map from x to 0, infinity, which are continuous. Okay, and then the proposition 1 says the following. A collection f, capital F, in Cxx is pointwise equicontinuous if and only if for every epsilon positive there is a continuous function delta in Cx, such that if x and y belongs to x and distance between x and y is less than delta x, then distance between fx and fy is less than epsilon f of x for every f in capital F. Okay, here I will put less than or equal, but doesn't matter. It's the same thing. Okay, this is proposition 1, and I will explain how this proposition follows. Proof. Oh, okay, the first one to say is that we only need to prove the necessity. I mean, we only need to prove the necessity. So, then, suppose capital F is equicontinuous, pointwise equicontinuous. Then the following number, rho x, well, maybe infinity, but okay, the definition of rho of x is this: the eta positive such that distance between f of x and f of y is less than or equal epsilon over 2 for every f y belonging to the capital F product the bold x eta. This number is positive for every x in capital X. This follows because it's point-wide continuous, the F. Now, if there exists x in capital X such that rho of x is infinity, which is possible because we are taking the supremum, and the supremum may be infinity, okay? And then what happens is there is some x doing that. Then this means that this implies distance between f of x, f of y is less than or equal epsilon over 2, and and so, okay, sorry, this is for every y in x, because this is followed because the rho of x is infinity, and so, and therefore, distance between f of theta and f of y is less than or equal epsilon over 2. This is for every theta and y in x, and for every f in capital F, and here is for every f in capital F. Okay. This followed by the triangle inequality using the over the point f of x, and then every delta in C of x satisfies the conclusion of the proposition. So, therefore, we can assume that rho of x is less than infinity for every x. This allows us then, okay, this allows to define a map rho from x to 0 infinity, even by the taking x into rho of x. Okay. Now the point is this rho is upper semi-continuous. Let's see. Rho is upper semi-continuous. Okay, to see this, fix x in x and delta positive. Now you take this number eta equal rho of x plus delta over 2. Okay, with this number we have, okay, you see, this number rho, this eta, what happened with this eta? You see, because this is not the supremum, because we are adding delta over 2 to the supremum, then this implies there are f and y in what? In capital F product, the bold x eta, such that distance between f of x and f of y, this is bigger than epsilon over 2. Okay, repeat, this follows because this number, this number is not the supremum. Okay, since it is not the supremum, the property breaks the definition of rho of x, and therefore we have this. Okay, then since f is continuous, we can find a neighborhood u of x such that, because you see this number is fixed, and then if u is very close to f, and then we still have this f of theta, f of y is bigger than epsilon over 2 for every theta in u. But you see, the y belongs to the ball. You see, the y belongs to the ball. So if we put u very small, very close to x, so shrinking u if necessary, we still have a distance between zeta and y less than eta for every zeta in u. Okay? Combining this and this, we get what? Then, and the definition of rho of theta. What happens with rho of theta? Will be less than or equal eta. This is for every zeta in u. But you see, eta is what? Is rho x plus delta over 2, which is less than rho of x plus delta. And then we have found a neighborhood u of x such that this inequality is true for every zeta u. So the rho is upper semi-continuous. Okay? Then the map gamma from x to r, defined by gamma of x equal minus rho of x, is lower semi-continuous because it's the negative of an upper semi-continuous function. Okay, and also alpha of x is bigger than gamma of x for every x, where alpha of x is equal to 0, the zero function. This is because rho is positive. Now we apply, this allows to apply Docker lemma you can find this lemma in reference Li, Nguyen, Yang. This paper is DCDS 19, sorry, it's not 19, 2017. Okay, we get it's allowed to apply Docker lemma to get a function, continuous function beta, continuous, such that alpha x is bigger than beta x. This is bigger than gamma x for every x in x. But now we define delta equal minus beta. Okay, and this function, what happened with this function? Delta belongs now. Delta is positive and continuous, so this belongs to here. And also, delta is less than rho. This comes from the definition of gamma. And so, delta satisfies the conclusion of the proposition. This complete the proof. Okay. Okay, the idea is this. So what we get that point-wise equicontinuity is equivalent to, for every epsilon positive number, there is a function such that distance between x and y less than or equal delta x implies distance between f of x, f of y is less than or equal epsilon for every f in capital F. Okay, now the idea is to replace. Now we are going to replace this number by a function. We are going to replace by a function. So this implies the following definition. We have now a definition. We say that the collection F is topological equicontinuous if for every function epsilon there is a function delta such that if x and y belonging to a capital X satisfies distance between x and y less than or equal delta x, then the distance between f of x, f of y is less than or equal epsilon f of x for every f in capital F. Got it. Now, obviously, or applying proposition 1, we have that every topological equicontinuous subset of continuous maps is pointwise equicontinuous. The converse is not true. The converse fails. Okay? However, we have the equivalence in compact. When compact X, we have the equivalence between equicontinuity, pointwise equicontinuity, and topological equicontinuity. Those are equivalent. Those properties, these properties are all equivalent in the compact case. Okay? Now, in general, we can compare topological equicontinuity with equicontinuity. Then comparing equicontinuity with topological equicontinuity. What happened with this comparison? Okay, when we do that comparison, we just know the following. Equicontinuity must apply to uniformly continuous map only. Uniformly continuous maps only. Then it's easy from this. Then it is easy to find collection. Of topological equicontinuous maps which are not equicontinuous. And here I have to amend here this way. Collection of equicontinuous, topological equicontinuous easy to find topological equicontinuous collection of maps which are not equicontinuous. Just pick a collection where with one member not uniformly continuous. Okay. Conversely, there are what? Equicontinuous collections which are not topological equicontinuous. The example, you just pick up X equal the Euclidean R and F as the sequence of maps Hn of X equal X plus n. This is for every Xn belonging to capital X plus n. Okay? Here X is equal R, so no problem. It's easy to see. Okay, to see this collection is a continuous easy because those are isometries. To see it's not topologically continuous, okay, easy. F is equicontinuous. Now, to see f is not topological equicontinuous, we just do the following computation. Take function, continuous function R to R, such that positive function, such that epsilon of theta go to 0 as modulus of theta go to infinity. A graph of the map, maybe this is a ring Gauss, Gauss ring, something like that. Okay, maybe like that. This go to 0 as theta go to infinity. Here minus and here go to infinity. Okay, easy to find a function like that. Now, given, suppose f is topologically continuous. This is by contradiction. By contradiction, suppose f is topologically continuous. Then for this epsilon, there is a delta, a continuous function, again positive in R, doing given by this property. Okay. Now what? Since delta of 0 is positive, there is y different from 0, such that modulus of y is less than delta of 0. Then 0, which is less than modulus of y, because y is non-zero, this is equal modulus of hn of 0 minus hn of y for every n. This is for every n. Okay, and by the topological equicontinuous property, we have this is epsilon less than or equal hn of y, which is what? Oh well, you can put y or 0, and here we'll put 0. Okay, hn of 0, which is epsilon of n, this doesn't matter. If you put y, is the same thing, and this go to 0 as n go to infinity by the choice. Then this is a contradiction. So f is not topological equicontinuous. Now I will give let's keep a sufficient condition for a continuous subset of continuous maps to be topologically continuous. Recall f is non-expanding if a distance between fx, fy do not increase with iterate. This includes this is for every x and y in x. This includes many like isometries where the distance is equal. I mean, invariant distance, isometries, contraction, etc. etc. So there are many examples of those maps. And then the proposition 2 is this: every pointwise convergent sequence of non-expanding maps is topological equicontinuous. Okay, this to see the difference between this proposition and the example, the previous example, just know that the previous example, in the previous example, what happened? This sequence is a sequence of isometries, therefore of non-expanding maps. The only difference that these don't have any pointwise convergent subsequence. That's why the proposition cannot be applied. In fact, cannot be applied because the collection is not topologically continuous. So this serves as a countersample for this proposition if the sequence do not converge pointwise. So how we prove this proposition? Proof. Okay, let Fn be these will converge pointwise to some f, and those maps are non-expanding. Now, take epsilon in continuous math of x, positives, and fix this. If x in x and a sequence and I going to infinity satisfied, epsilon of f and I of x go to 0 as I go to infinity, then because the convergent pointwise you will have epsilon of f of x is 0. Okay, by continuity. I mean, because the pointwise convergence, this go to f of x, and because epsilon is continuous, you will get this, which is a contradiction that epsilon is positive. Okay, so this implies that the infimum of x epsilon of f of n of x, given that n belongs to n, this is positive for every x. Okay, now, as before, I will define some map here. I mean, I will define this x of gamma x equal minus infimum of epsilon of f of n of x, given that n belongs to n. Okay, this map is this gamma is lower semi-continuous. Okay, and alpha x is bigger than gamma x for all x belonging to R, where again alpha of x equal 0. Then Docker lemma, as before, provide continuous beta, okay, continuous, such that alpha x bigger than beta x bigger than gamma x for every x. Okay, so taking what? Taking delta equals minus beta, we get delta belongs to C of x. And if x and y, I mean, distance between x and y less than delta x, then distance between fn of x, fn of y, this is less than or equal distance between x and y, because fn is a non-expanding, this is less than or equal delta x because of this. But this is because of the definition of a gamma. We will get this epsilon fn of x. This is for every n. Okay, so f is topological equicontinuous. Okay, there are two examples to apply this property. We have two examples. Example 1, okay, in R, x equal R, the Euclidean space. Okay, the first is Gn to define this sequence 1 over nx. This converts pointwise to 0, and also is not expanding, and this is non-expanding sequence converted to 0 pointwise. Therefore, the sequence is topological equicontinuous. The second example is fn of x equal x plus 1 over n. This converts pointwise, in fact, uniformly to the identity. And again, those are isometries, therefore non-expanding. Therefore, GFN is also topologically equicontinuous. Okay? There are one more example here to avoid the confusion, because a third example, which is different, is Fn of x equal n for every n is topologically continuous, but has no pointwise convergent subsequence. Sorry. Convergent subsequence. This conclusion is not obviously because of the proposition 2, but this is an exercise. See this? You cannot use the previous proposition because this sequence have no pointwise convergence subsequence. Okay? Those examples follow the topological equicontinuity in both examples, follow because of the proposition 2, but not here. And here, no, proposition 2 is not applied here. This is an exercise. Okay. Now we will talk about the tilde convergence. Okay. What is the idea here? We know that uniformly convergence sequence of continuous map of uniformly continuous is equicontinuous. This is an exercise for those people who have been already studied Arcel's-Colli theorem. Okay, what happens if we remove here uniformly here? When we have removed this, okay, we have this following statement: uniformly convergent sequence of continuous map still have some property related to equicontinuity, which is pointwise equicontinuity. This can be also proved using the same argument as the previous statement. Now, the examples. Okay, I will put 2 and 3, which example I'm talking to. This example. Okay, I will put example star here. Okay, here, and okay, I will remove this. Example star support the idea that uniformly convergent sequence of continuous map is topologically continuous. We already know they are pointwise, but also those examples support that idea because in both examples we have topological equicontinuity and both examples converge uniformly. Okay. Now, then the problem now is the problem which convergence implies topological continuity. This is a problem. Okay, here we are saying that uniformly convergent perhaps guarantee the topological continuity, but we don't know. Then I will suggestion is the following definition: a sequence Fn converges, or tilde converge, sorry, tilde converge to F. We are not assuming nobody here is continuous, nothing, and the definition is if for every epsilon positive continuous function of R there is an n natural number such that distance between Fn of x, f of x less than or equal epsilon Fn of x for every x in capital X. We say that Fm is tilde convergent if Fm tilde converges to F for some F. Okay, I will make a remark here. We can replace epsilon Fn of x by epsilon f of x without altering the definition. I mean, we can, instead of this guy, we can put this guy, and the definition is the same. Okay. The first to say that tilde convergence implies uniform convergence. This is easy to see because in this definition we can put here a constant map, positive constant, which means a positive number, and then you get uniform convergence put in there. This is false, the idea. However, this is false. And the countersample is this. Countersample is the sequence function x plus 1 over n. Okay? This is given in the previous example. Okay? Exercise. Show this Fn is not tilde convergent. Actually, do not have any tilde convergent subsequence, actually. I will stop now. Thank you.
Rescaling equicontinuity. This is part 2. Last part, we stopped in the definition of tilde convergence. We defined sequence f of continuous function, sequence of function, not necessarily continuous, converge tilde to f if for every epsilon function there is a delta function. Sorry, there is an integer. There is an integer, positive integer, such that if a distance of x and y less than or equal delta x, then I'm sorry, it's confounding. If n is bigger than or equal to capital N, then distance between Fm of x and f of f is less than or equal epsilon Fn of x. This is for every x in capital X. And we observed this is stronger than uniform convergence. I mean, tilde convergence implies uniform convergence. But the converse is false. We mention a counterexample. This is false. I will not mention the counterexample here because it's in part 1. Now, now I will present a sufficient condition for a sufficient condition for uniformly convergent sequence to be tilde convergent. Okay, recall metric space X is proper if every ball of finite radius is precompact. Okay, and a map from X to X is bounded if the image of X have finite diameter. Okay, and the proposition now is this, proposition 3. If a sequence Fm of function, continuous function, functions, maps, better to say maps, converges uniformly to a bounded map F and the space is proper, then the sequence Fm is converged in the tilde way to F. Okay. So this is give a condition for uniform convergence to be to generate a tilde convergence. The proof. Okay. Since Fm converges uniformly to a bounded map, we have, there is N1 a positive integral such that the diameter of this set Fm of X, given that X and N belongs to the space product, the interval N1 to infinity, this geometry is finite. I mean, in some sense, the Fn are uniformly bounded. Okay, now fix epsilon in Cx. Since X is proper, the above inequality provides epsilon 0 number positive such that epsilon 0 is less than epsilon theta. This is for every theta belonging to this set. Fn of x, given that xn belongs to x product and 1 infinity. How we get this? Because this condition implies that the whole image of Fm given n bigger than n1, all are doors contained in a single ball, and the ball, that ball is compact because of the proper hypothesis, and since epsilon function, I mean, is continuous, it have a positive, he have a lower bound, a positive lower bound because of compacity. Okay, that's why appears the epsilon 0. Next, for this epsilon 0, okay, since Fm converges uniformly to F, there is M2, another positive integer such that distance between Fm of x and Fx is less than epsilon 0 for every x n belonging to x product and 1 to infinity. Okay? Now we take n equal the maximum, the max in between n1 and n2. If n is bigger than equal n and x belong to x, then distance of Fm of x and Fx is less than epsilon 0. This is because just n is bigger than n2, and here we use this. So here is 2. Okay. If, on the other hand, okay, sorry. Now we have this. That is since n is equal to n2. However, since n is also bigger than n2 and than n1 because of the definition, we also have that epsilon 0 is less than or equal, or less than, than epsilon Fm of x. And then we plug this and this, we get distance between Fn of x, Fx of f of x is less than epsilon fm of x, and this is for every x. And therefore, the convergence is tilde convergence. Therefore, fm converges tilde to f. And this completes the proof. Now we can apply this proposition neither we cannot apply this proposition to the previous example. Yeah. Because because what? In those examples, the convergence, in one example, the convergence is not uniform, and in the other example, the limit map is not bounded. Okay. However, but we can apply it to which example? The next example, to the example fm of x equal 1 over n. This is a sequence of continuous map in the Euclidean R. In that case, fm of converges uniformly to 0. Okay. And this, which is bounded. The 0 map is bounded, and therefore the sequence fn is till what we have is fm converges tilde to 0. Okay. Now I will give the main motivation for the introduction of tilde function, tilde convergence. Then we have a theorem here. Every tilde convergent sequence of continuous map is topological equicontinuous. Okay. The proof. Okay, let fm, the sequence of a continuous function, converging to some function f. Okay, since tilde convergence implies uniform convergence, we get that the map F is continuous. If the Fm were uniformly continuous, the limit is uniformly continuous. But here, what we get is only continuity. Now, fix a function epsilon, a positive function in the reals, I mean, to the positive reals, and okay. We can apply now, there is a lemma here by well-known result. This is which well-known result? This is lemma 2.8 in reference Li, Nguyen, Yang. This is the reference, this lemma. By this lemma, we can find, by this lemma, there is a positive function, x, gamma, such that gamma x is less than infimum of the epsilon y, given that y belongs to the ball x gamma x. Okay? I will signalize this as a star here, this equation. By using this, Fm converts tilde to F, we get what? We get an integer n such that if n is bigger than n, then the distance between Fm of x and Fx is less than the minimum between gamma Fn of x divided by 3 and gamma f of x. Okay? Actually here, to get this, we get the remark by the remark, given the remark we do before, immediately after the definition of tilde convergence. Okay? Now we are going to apply the continuity of f, since f is continuous. There is also this delta zero in a continuous function, positive, such that if the distance between x and y is less than delta x, then distance between fx and fy is less than gamma fx over 3. Okay? Now I will going to use that since f1 until fm-1 are continuous, there are also delta 1, let me put there here, delta 1 until delta m-1, those are continuous function positive, such that the distance between x and y less than delta n of x implies that distance between fm of x and fm of y is less than epsilon fm of x. Okay? And this is for every n in between. This is for every n in between 1 and n-1. Okay? And now I will take delta equal the minimum between the delta 0 and delta 1 until delta m-1. Okay, capital M-1. Then this delta is not only continuous but also positive. If, then we are going to proceed as follows. If the distance between x and y is less than delta x, Okay, and also, okay, n is equal, belongs to 1 until n minus 1, then we just get this fm of x, fn of y, less than epsilon fm of x. This is because of this. You see, because of this. Now, if the distance between x and y is less than delta x, and n is bigger than equal n, then we are going to do apply the triangular inequality. Fn of x, fn of y is what? Less than or equal to this, fn of x, f of x, plus distance between f of x, f of n of y, f of y, and this plus distance between f of x and f of y. This is because of the triangular inequality. We go further. This is less than. Now we are going to apply the fact this n is bigger than n, capital N, and then we get appear here gamma fm of x over 3. Here appear gamma fm of y over 3, and here appear gamma of x over 3. Here appear this is controlled by this, because this delta is less than delta 0, okay, of x. And we apply this property here, okay? Now, these three sum members is less than or equal to what? To the maximum between gamma fn of x, gamma fn of y, and gamma of f of x. Now we are going to consider the three cases, because this maximum, what happened? The maximum may be, okay, but let me remember something. Okay, let me remember also that we have this fm of x, f of x is less than gamma f of x. This is because of the star equation. By star, I will remind you, star here. Wait a minute. Where is the star? Here. You see, not precisely star. This by this equality. You see here you have this minimum members to minimum, and this is the reason why appears this inequality. Okay. Then, okay, fm of x belongs to the ball f of x, gamma f of x, and so now star implies what? Implies that gamma of f of x is less than epsilon fm of x. Okay. Next, okay, let's keep this in waiting model. Now we have three possibilities for the minimum. We have three possibilities for the minimum. maximum, sorry, for this maximum. Possibility one, the max may be gamma Fm of x, and this is easier because in this case we have distance between Fm of x, Fm of y is less than gamma of Fm of x, and because gamma is less than epsilon by star, we get this, and nothing to prove. The second option, the max equal gamma of Fm of y. Okay, in this case, then Fm of x belongs to the ball Fm of y gamma Fm of y. Okay, and so a star again implies what? Implies that gamma of Fm of y is less than or equal than Fm of x. Thus, distance between Fm of x, Fm of y is less than epsilon Fm of y, x. Okay, finally, we consider the case when max is equal gamma f of x, but this is already controlled by which one? This is already controlled by this. Okay? By this, which I say to you to keep an eye, okay, by this. Then we have distance between Fm of x, Fm of y, less than what? Gamma of f of x, which is less than epsilon Fm of x. Okay, all three cases implies that the Fm is topological equicontinuous, and this completes the proof. Okay, this finished the part 2. Thank you.